Now today we are going to talk about L'Hopital's rule, which is a favorite among calculus students. We often, in my past, we often call it the hospital rule, but it's actually pronounced L'Hopital, I guess. So we will say it like they want us to say it. To see L'Hopital's rule, let's flip to the next page. We're on page 455. Where L'Hopital's rule is stated for the 0 over 0 case, which means what the 0 over 0 means that if f and g are functions that are both equal to 0 at a point A, in that case, and of course f and g has to be differentiable in an open interval containing A, except maybe at A. Then if the f and A are both 0 as x approach A, the limits are, then we have this interesting situation, which is the first case of the L'Hopital's rule, which is, actually all cases says the same thing. That is, the limit of f of x over g of x equals the limit of the respective derivatives in the same ratio. That is, it equals the limit of f prime of x over g prime of x. If f of x, if the limit as x approach A of f of x goes to 0, and the same as g of x. That is, and that's very important. The L'Hopital's rule only applies if f of x goes to 0 or g of x goes to 0. In this case, this is called the 0 over 0 case. Okay, this is not dividing by 0. This is merely stating, this is a shorthand to say that f of x is going to 0 at A, and so is g of x. They're both going to 0 at A. When that is true, and then we have the interesting situation that this limit is the same as if you were to take the derivative of the numerator and the denominator. And to be clear, do not confuse the L'Hopital's rule with the quotient rule. The quotient rule is a completely different story. This simply says you take the top derivative of the top over derivative of the bottom, and that will be the same as calculating the original, especially, well, being that the original has a 0 over 0 case, that would be difficult to calculate. The reason we take derivative is that it often turns into a simpler matter if you take derivative of this thing. So that's why we're doing it. Now the first thing we want to do about the L'Hopital's rule is prove it. Okay, so let's look at the bottom of the proof. Now the proof, of course, we have to assume that everything is all these functions are continuous over some open interval. And we also assume that the limits we assume these things are equal to 0, and so on. Okay, things are continuous. And also we know that we also assume this. Well, being that things are continuous, we can deduce that f of A equal to 0 and g of A equal to 0. That is, we are proving a simple, a simpler case, okay, without worrying about certain exceptions and details. We'll just simply assume that this is the case, that not just the limit of equal to 0, but that it actually equal to 0 itself. And so we will prove a simple case of the L'Hopital's rule. And so let's look at the next page, and we'll go ahead and do the proof. Now the proof says that, how do we do the proof? Now given this, the proof is actually short and sweet. So we will start with the function we're trying to prove here. The limit as x approaches A of f of x over g of x equals to, first we will, being that f of A is 0, okay, then we'll do that subtraction. F of x minus f of A over, and then g of x over g of A. All right, so we have this situation going on, and being the f and g available 0. So this equation stands, right? So, okay, so far so good. The next thing we're going to do is something even nicer. Is we will continue and divide each numerator and denominator by x minus a. So we'll write it down. It's quite a bit to write it down, but the concept is actually very plain. Okay, we'll divide everything by x minus a. So there's g of x minus g of a divided by x minus a. All right, so far so good. We're dividing both things by x minus a. And what is that? So then at this point, we can rewrite this as being there's a limit of two quotients, and we can rewrite it as two limits. So we'll copy this whole thing again. That equals the limit. The only thing I'm doing is adding limit to all the stuff. Okay, let's write this whole thing once again. So f of x minus f of a over x minus a, and then g of x minus g of a over x minus a. And both limits has x approach a, which is what we've been doing this whole time. All right. So now we have, so the equation, our equation is looking much longer, but actually it's much neater. Because what is this thing? Now if you look at this thing, you recognize that's the definition of f prime at a. The derivative of f of a at a is this thing, right? Similarly, this is the definition of derivative g prime at a. The denominator is. Okay, that's how what we had some time past. All right, so that equals to this. That's that fraction, the definition by the definition of the derivative. And then we'll keep going. Now, what is f prime of a? Well, the f prime at a is the same as the limit as x approach a of f prime of x. That's why? Because the function f prime is all assumed to be continuous, so that relationship holds. And the same at the bottom. Limit the g prime of a is the limit of g prime of x as x approach a. So what is that? That is actually, is that our answer? Okay, then one more step. So we'll the limit of the quotient, we can take the limit out because everything's continuous and all. So that equals the limit of f prime of x over g prime of x as x approach a. So that is completes the proof. That's what we were trying to prove before. See, right here, the f over g is the same as f prime over g prime as x approach a, and we have arrived at that answer. So that concludes the proof of a simple case of L'Hopital's rule when everything's continuous and differentiable and all. And then and this is the 0 over 0 case. Okay. Now let me erase the board. Now, to see an example of how to use the L'Hopital's rule and its advantages, let's look at the next example. Example 4.38, which is on page 456. So, example 4.38. My board is still a little wet. Let me wipe it. Now, I'm assigning 4.38, example 4.38, part A and part B as part of your homework. So let's turn the page and then we'll continue doing part C. Now, part C, which is a cute little problem. So part C, we'll calculate the limit, or find the limit as x approach infinity of e to the 1 over x minus 1 over 1 over x. All right. So remember the L'Hopital's rule, we have to have the 0 over 0 requirement. Okay, well, does this suit the 0 over 0 requirement? X goes to infinity, 1 over x goes to 0, e to the power 0 is 1. 1 minus 1, 0. So the top equals 0. Again, as x approaches infinity, 1 over infinity is going to go to 0. So 0 again. So it does fit the L'Hopital's requirement. So having said that, then let's take the derivative. So when you take the derivative of this thing, of both the top and the bottom, so let's take the derivative, then it equals to, of the top, then we have the derivative of e is e itself, okay, e 1 over x. Then the derivative of 1 over x is minus 1 over x squared, okay. And then derivative of 1 is just 0. Similarly, on the bottom, the derivative of 1 over x is minus 1 over x squared. All right, so far so good. And then we cancel out the minus 1 over x squared. Then we get only e to the power 1 over x. As x goes to infinity, 1 over x goes to 0. So we get e to the power 0, which is 1. And that's the answer. See, a neat little answer and a quick little problem. So, and next, let's look at problem number D. Problem number D says, okay, sine part D says, we'll do the limit as sine of x minus x over x squared. All right, so then as x approaches 0. Now, is this a 0 over 0 case? Again, let's check. As sine goes to 0, sine of 0 is 0, minus 0, that's 0. So top is 0. So as x goes to 0, x squared is also 0. So 0 on the bottom, so it fits the L'Hopital requirement. Therefore, we shall take the derivative, okay? And then, so that would be equal to the limit. Did I forget the right limit here? Yeah. The limit as derivative of sine, we'll do the write down cosine x minus 1, that's 2x. All right. And as x approach 0. Now, as x approach 0, cosine 0 is 1. 1 minus 1, 0. The bottom is still 0. So we are not getting anywhere because we're still at the 0 over 0 situation. And so what is the limit? So what we do is we take another derivative. So we'll do it again. Apply the L'Hopital's rule again. Take the derivative of this thing. Then we get the limit cosine becomes derivative of cosine is negative sine x. And then the derivative of 2x is just 2 as x approaches 0. Now that is, okay, that looks pretty good. And then as x is 0, sine of x is 0. And the bottom is 2, so the answer is a neat little 0. See? A very quick, easy problem. That's why L'Hopital's rule is very popular with students, because it's having a good time, right? So let's look down at so far we have covered the 0 over 0 case. Next thing we need to look at is the L'Hopital's rule of the infinity over infinity case. That is, what happens when f of x and g of x are both going to infinity? Well, when that happens, the rule stands. Okay, the same rule. That is, if it's an infinity over infinity case, then the L'Hopital rule works just like it's been working with the so far. And that's the infinity over infinity. So the L'Hopital rule therefore works whether it's 0 over 0 or infinity over infinity. All right, now the next question you have is, what about other situations? Nope, this is about it. Okay, L'Hopital's rule works for two cases, either 0 over 0 or infinity over infinity. It works exactly the same way. Now, the proof of infinity over infinity is not mentioned in your book, so I have it assigned as homework. So the homework part of the homework is on page 457 or 8, wherever this is, 457, proof theorem 4.13, which is L'Hopital's rule, infinity over infinity case. And then later in the homework, when we talk about homework, I will show you how I proved it. You will prove it based on the 0 over 0 case. You just use this to prove that. So, but for now, let's move on to look at another example. Okay, we're looking at example 4.39. So please do example A, 4.39a, as it's pretty straightforward, so that we will not spend too much time on that because that's the same problem we've already done. Okay, but it's nice to see your book, go over it a little bit, and then we'll go straight to example B. So we are at, this is example 4.39. B. So example 4.39b says, oops, here. Now we have limit as x approach 0 from the plus side of natural log of x over cotangent of x. All right. Now, first we check to see if it fits the criteria of the L'Hopital's rule. Well, as x approaches 0 from the plus side, the natural log dives down to become negative infinity. Okay, that becomes negative infinity. Whereas the cotangent, as it goes to 0, the cotangent graph, let me show you what remember the cotangent graph goes like this. Okay, so as it goes to 0, the cotangent goes to positive infinity. So as a result, it is the infinity over infinity case. It doesn't matter if it's positive or plus, the L'Hopital rule works. Yeah, so so then as a result, then we apply the L'Hopital's rule and take the derivative and come up with something. Okay, so let's take the derivative. It becomes, so that equals to limit. The natural log becomes 1 over x. The cotangent becomes, what was the derivative? The cotangent becomes negative cosecant squared. Now, if you don't remember that, that's a bit harder to remember. Just look it up, okay? The derivative of the cotangent is negative cosecant squared. At least that's what I remember, and also what your book says. All right, so then that equals to something. And what's x doing? X is going to 0. All right, so at this point, let's simplify this thing a little bit. So that equals to limit, okay? That's 1 over x, so we'll write down x on the bottom. Cosecant is 1 over sine, so you flip it around, so then we'll write it on top. So the sine squared x, being the cosecant equals to 1 over sine. All right, so to divide by a fraction, you inverse and multiply and flip it on top. And do we have a negative sign? Yes, we have a negative sign somewhere. We'll keep it. Don't forget the negative sign. So far so good. And at this point, x is still approaching to 0 from the plus side. Now, at this point, we have, as x approaches 0, this goes to 0, and so does this. Okay, so we're in a 0 over 0 situation. We applied L'Hopital's rule one time, and we have improved things somewhat. Okay, this looks quite a bit better than that. But we have not reached the goal yet. But because right now we have reached the 0 over 0 situation. So at this situation, we then what do? We take the L'Hopital's rule derivative again. Okay, so let's take the derivative of the top and bottom one more time. X 0 plus. Then the sine becomes cosine, and so on. Take the derivative, which is minus 2 sine. First, we do the power rule, 2 sine x, okay? And then the derivative of the inside, which is cosine x. And then the bottom is just 1 because it's just an x. All right, so now we have reached the end. We know we got somewhere, right? And then we evaluate this limit as x approaches 0, sine of x is 0. So that whole thing crashes into 0, and that's that. That equal to 0, period. And that is the limit of natural log over cotangent, which normally, if you were to look at it, you have no idea how do I do that? I have no idea, right? Because they're both going to infinity and you're at a total loss. But with L'Hopital's rule, then suddenly you cranked it out to be a nice, neat answer. So that's that's how wonderful the L'Hopital rule is. It's very convenient. Now, the L'Hopital rule isn't always easy to apply, but a lot of times it is. Now the next example is on the next page, 459, example 4.40 shows you an example when L'Hopital rule doesn't apply. Well, it doesn't apply if this situation doesn't hold. If the limit is not 0 over 0 situation or infinity over infinity situation, the L'Hopital rule just doesn't make any sense. And the example will show you that if you try to apply it, you'll come out with trash. Your answer is completely off and has nothing and makes no sense at all because, well, you're applying the wrong rule. It does not apply. Okay, now, so that's that. And the next thing we want to talk about is the next example. Next, let's look at example 4.41 on page 460. Now here's look at the example first. Let me write it down. Is the limit as x approach 0 from the positive side, x natural log of x. I should mention that the reason x approach from the positive side of 0 is because the natural log isn't defined for any negative numbers. It just doesn't make sense to define it. So that's why if it's natural log, you always see something like this. So anyway, we have this thing, and then we need to apply the L'Hopital's rule, okay, which is either 0 over 0 or infinity over infinity. Well, but this has no fraction in it. So what do? Then we force a fraction into this thing in order so that we can apply the L'Hopital's rule. And the fraction we're going to force is this. This equal to the limit of, we'll keep the natural log on top, because the natural log is harder to manage. And we'll force the x onto the bottom of the fraction by this. See? To divide is to invert and multiply, right? So we can push that thing down, becomes 1 over x on the bottom. And once we did that, and we check it out, as x is still approaching 0 from the positive side, well, as x approaches 0, the natural log goes to negative infinity. Now remember what the natural log graph looks like. It looks like this. So then as it approaches 0, it just takes a deep dive. So then that goes to negative infinity, whereas as x approaches 0, this goes to, well, positive infinity. So that's an infinity over infinity situation. Doesn't matter. The sign doesn't matter. So that's how we know. That's how we know that's how we know that the L'Hopital's rule apply. And anyway, so that's that. And being that it applies, let's apply it. It equals to the limit, the natural log of x, take the derivative, that's 1 over x. The derivative of 1 over x is minus 1 over x squared. Okay, and then and so that there's an interesting fraction for you to fix. But by the time you fix it, that equals to the limit. You have x on the bottom and then x squared on top. Okay, keep the negative sign, which is just x. And the limits x approach 0 from the plus side. So if it's just x, then we have, where's my negative sign? Yeah, don't forget the negative sign. There we go. So the limit will be equal to 0. That's the answer to this very interesting situation where you have, well, if you look at the original thing, x is approaching 0, natural log of x is approaching infinity, negative infinity. This is basically a 0 times negative infinity situation. And what's that? You have no idea until you pull through the L'Hopital's rule and then come up with the actual answer is 0. And the L'Hopital's rule isn't obvious at first until you force it. Force it into a fraction. If it's not a fraction, you need to beat it into one. So that's how we do this. That's example 4.41. So let's look at the next one. The next example is next, let's look at example 4.42 on page 462. It says we to evaluate the limit as x approach 0 from the positive side of 1 over x squared minus 1 over tangent x. All right, now when you look at this problem, you think, what about it? Well, what about it is that this 1 over x squared is will go to infinity, and you minus 1 over tangent x. Tangent x at 0 is also that also tangent of 0 is 0, so this also goes to infinity. So this is a situation where infinity is minusing subtract infinity. And you say, well, wouldn't that be 0? You know, they take each other out. No, that's not how it works. First, always remember infinity is not a number. You cannot subtract it. And for another, one infinity might be a whole lot bigger than the other, okay? Or they might be the same, or they might be some other any number. This can be anything. And it depends on how this works out. So, and that's what we're going to work it out. We're going to figure out what this thing is. And to do that, we will apply L'Hopital's rule. But the problem is L'Hopital's rule requires us to have a fraction of some sort. So we don't have a fraction, so we'll beat it into a fraction. So let's try that. And in this case, these are two fractions, so we'll take the common denominator, then it becomes one nice fraction. So let's do that. And forcing it into a common denominator, we have multiplying the bottom together, okay, tangent x. And the top becomes 1 times tangent x minus x squared. All right, that's how you come. That's just the basic rule. So let's move along. Moving along, then what about this situation? Then as x goes to 0, that's 0, that's 0, that's 0, and that's 0. They're all 0. So we have now reached the 0 over 0 case, which means we can apply the L'Hopital's rule. So let's apply it by pulling off a bunch of derivatives. Okay, so applying the L'Hopital's rule, we get limit as x approach 0 from the plus side. We have tangent x, derivative of tangent is secant squared, minus 2x, and then what is that? That is x squared tangent squared. Right, that's a multiplication, so we need to do the product rule. To do the product rule, we'll do x squared, the first term times derivative of the second, which is again secant squared, plus the second term, tangent x times derivative of the first, which is just 2x. And that is the derivative comes out. And what do we have here? As x approaches 0, we check what happens when x is approaching 0. As x approaches 0, this the top then approaches secant of 0. Secant is 1 over cosine. Cosine of 0 is 1, so secant of 0 is also 1. That's 1 minus 0, so this approaches 1. Okay, we'll say this approaches 1. Like that. And as this approaches 0, that first thing is 0 here. Second thing is also 0 here. So that the bottom will approach 0. So at this point, then, so when in a limit, when the top approaches a fixed number and the bottom approaches 0, then the whole thing approaches infinity. Therefore, this equals to infinity. And that's the limit of whatever we've been doing. What we've been doing? That thing, okay? The limit of this end up equal infinity. See, like I said before, infinity minus infinity can be anything. In this case, end up being infinity. That's because infinity is not a number, okay? Always remember that. because I all right, next, let's look at example 4.43, which is the yet another problem where we have a function raised to a different function, something like this, okay, where f of x, you're supposed to take the limit of where f of x has some kind of g of x on top. Now that looks very complicated, so let's see how to tackle such a thing. Now to calculate something like that, let's look at the example where we're supposed to calculate the limit as x goes to infinity of x raised to the power 1 over x. Okay, now that looks okay. As x goes to infinity, 1 over x goes to 0, so you basically have something like infinity to the power 0, and what is that? Who knows, right? So we need to have a trick to know how to do that. And also, that doesn't look anything like a fraction. How would you even beat that into a fraction? Well, the trick is, anytime you have some kind of a power, the common trick is use the natural log on it. And to be exact, let's look at this. Okay, first we will let the variable y equal to x to the power 1 over x, and then we are going to okay, so then we'll take the natural log of this thing. Fine. So natural log of x to the power 1 over x, by the rules of the natural log, anything on top can go in front. So that equals to 1 over x natural log of x. And that looks like a fraction, okay? Which is, and then we'll figure out what happens to this thing when x goes to, what was it? Infinity. Okay, so we'll calculate the limit of this thing as x goes to infinity. I'll write down the limit here. X goes to infinity. And to calculate the limit, as x goes to infinity, that goes to infinity, that's infinity, and we have a fraction. So we have the infinity over infinity situation here, which means we can apply the L'Hopital's rule. And therefore, we will apply it. To apply natural log of x, we still have the limit here. That becomes 1 over x, taking the derivative. And the bottom is just 1, okay, as x goes to infinity. And that would be, what is that? That would be 0. All right, so far so good. Now, but so far, we only know what happens to the natural log of this thing. So in other words, see, we set y equal to that. So the natural log of y as x approach infinity equals to 0. But what happens to y itself? If the natural log goes to 0, that means what? That means y itself goes to e to the power 0. Okay, like anytime the variable, the log of the variable approach is getting close to 0. How does that happen? Well, that means the variable itself must be approaching e to the whatever is approaching. In this case, e to the power 0, which is 1. And that's the answer. Okay, so that's the trick you use. But you because you use the natural log, you have to later use e to reverse the process, and then that's the answer we get. Okay, a very short, neat solution to a very tough-looking problem. All right, so next, let's look at example 4.44. Now, example 4.44 says we need to do something called the limit as x approach 0 from the plus side of something such as x to the power sine of x. Now, as x goes to 0, that x is 0, sine of x is also 0, so you're getting something called is a 0 to the power 0 situation. What is 0 to the power 0? Nobody knows. Okay, it's not defined. So we're kind of in a bind here. So what we're gonna do is borrow L'Hopital's rule. But being that this is a function in the f of x to g of x format, we will use the natural log to bring this thing down. Okay, the purpose of the log is to take the exponent down so that we can mess with it. So to take the exponent down, we will do the same trick that we did in the previous example and let y equal to the function. Y equals to sine of x to the power sine of x. Well, anyway, so that's that. And then we'll take the log of this thing. So the log of it, the natural log of x to the power sine of x, we're using log for that convenient situation where you can take the exponent right down, okay, and put it in front. So e equals the sine x log natural log of x. Okay, so far so good. And then, but remember that we have taken the log of this function. So when we, once we get to the solution, we have to remember to reverse it back to by using e is e to the something. But in the meantime, let's figure out where that goes. Once we figure that out, we can figure out where the other thing goes. What is that? So sine of natural log of x, that's just a product, okay? But to use the L'Hopital's rule, we need a fraction. How are we going to do the fraction? Well, one way is that we can push, one of these things got to be pushed to the bottom, okay? We can push the natural log to the bottom, but that, if we did that, we are going to, let's see, what did the book, the book tried that and landed in a worse place than before. So we're going to skip that trick and push the sign to the bottom, okay? So let's push the sign to the bottom, and that equals to the natural log, ln of x, divide 1 over sine. 1 over sine is cosecant, so we'll write it that way, CSCX, where we're doing the limit, okay, we're still doing the limit as x approach 0 on the plus side. All right, so that is, and once we did this thing, let's check this. As x approaches 0 from the plus side, the natural log goes to minus infinity. Okay, the cosecant is 1 over sine. It also goes to sine of 0 is 1 over 0, and that also goes to infinity. So this thing is an infinity over infinity situation. Therefore, we can apply the L'Hopital's rule. And so let's take the derivative. To take the derivative, we get limit of let's see, where did it go? That is that's 1 over x. Okay, the top becomes 1 over x, and the derivative of cosecant is negative cosecant cotangent. CSCX cotangent x. So that's so far so good. Which equal as x approach 0 from the plus side. Now to simplify matters, we're going to pull some trigonometric skills, whereas and rewrite this thing to make it look better. All right, that's limit. How much space do I have? Maybe there's enough. So the limit of cosecant. We'll write the x on the bottom. Cosecant is 1 over sine, so we'll write the sine on top. And cotangent is 1 over tangent, so we also write. Actually, we will write. Let's see. Well, cotangent just go up there to become tangent. All right, so far so good. And the limit still applies. And then we have this situation as x approach 0. Now at this point, we'll break it down into 2 limits, because as x approaches, well, it doesn't matter. The point is we're going to break it into 2 limits, because one of the limits, we know what it is. So this equals the limit as x approaches 0 from the plus side, sine of x over x as x approaches 0. And then the other one we'll write down as limit of as x approaches 0, tangent of x. Now the sign of x over x is something, the limit as x approaches 0 is something that we've encountered a couple of times now. And the result is 1. Okay, sine x over x is 1 because at 0, the sine graph goes like this, okay, goes up and then turn down, whereas the x graph just goes straight. So at 0, their ratio is 1. So that's how you remember it. So this limit equals to 1. This equal to 1, and that limit as tangent approaches 0, tangent 0 is just 0. So it's 1 times 0, and the answer is 0. Now, if so, the natural log approaches 0, which means the function itself approaches e to the power 0, which is 1. And that's the final answer for the example. All right, then whenever you apply the natural log to do the L'Hopital's rule, don't forget to slap on the e, to get it back, because you apply the log, you got to do the e to be fair, right? And it's not like you just did the log for nothing. So once you get the log, then you put on the e, and the answer is 1. So this complicated-looking exponent at the answer of this complicated limit is actually 1. Now that's very neat. All right.